Sustainability. What does it actually mean? And what does a sustainable world really look like? But more importantly, what comes after sustainability as we understand it today? I would like to share with you my perspective on sustainability and beyond, and why chemistry sits right at the heart of this journey. My name is Rosa Arigo. I'm a chemist by training, and I work in education and research. Over time, I came to the conclusion that for a truly sustainable future, it is not sufficient that our economies, our technologies are efficient, eco-friendly. They need to be resilient. They need to be adaptable to changes quickly, to renew, to regenerate. And the same is true for our sciences, our education. But in order to do that, we need to think outside the box. We need to be creative. A creativity that is grounded in a deep understanding of how nature works. So my message for today is that we need scientific knowledge, we need creativity, and we need everyone to be involved in the process. So science and art, can they come together? The answer is yes. I was a very creative child myself. I used to daydream about becoming a fashion designer. And at 5 years old, you would find me always drawing around. I still do that. But chemistry was always around me. I recall my father telling me some stories. He was working for Pirelli, the company that makes tires for cars, and he would tell me about this chemistry lab where rubber samples were made, tested. Sometimes they worked better, sometimes not. But then I knew a different story about chemistry. In the village nearby where I grew up, an oil refinery plant. And alongside stories of progress, there were stories about impact on human health, particularly newborns, and on the environment. So I understood very early that chemistry has a power, and power can be used in different ways. So the chemistry should not be defined by its worst outcomes, because chemistry has always served society. In fact, chemistry is key to delivering the United Nations Sustainable Development Goals. So this is why I study chemistry, because it holds the responsibility for making the world a better place. And this is what, in chemistry, I put my creativity. Now, today we talk about sustainability and beyond. It is therefore helpful to look back at how chemistry has served society in the past, in the present, and where we are going. And I will do that by focusing on an area I work in. This is catalysis. A catalyst is a chemical compound, in our case is a solid material, that is added to the reaction mixture. We call them reagent, feedstock, to speed up the reaction, and thereby making the process more efficient. This is why more than 90% of the industrial chemical processes are catalytic. Without catalysts, modern life, as we know it, would not exist. Likewise, it was very early understood that without natural catalysts, enzymes, there would be no life. One of the breakthroughs in catalysis was the development of the ammonia synthesis process. Ammonia is used in fertilizer. One single chemical process has helped lift societies out of famine in the early 20th century. Chemistry has always been connected to politics, to conflict. During World War II, the increased demand for fuels has led to the development of processes for the synthesis of liquid hydrocarbon. We call them Fischer-Tropsch catalysis. This is still being used nowadays. So the first half of the 20th century is dominated by petrochemistry, from natural resources, fossil-based resources, natural gas, oil, to the chemicals we need. It is in this period that we produce for the first time polymers. They have changed our life, the way we move. Think about cars. more plastic components, lighter vehicles, cheaper, everyone can buy one car. However, in the second half of the 20th century, the environmental costs of this lifestyle change could not be neglected. Air pollution, emission of toxic gas, health concern. So this is when our language starts to change. We talk about green chemistry now. For the first time, we use the term sustainability, sustainable chemistry, carbon neutral economy. We see the first biodiesel plant, we see the first hydrogen car. So if I can use the symbolism of a postcard to represent what an industrialized city was looking like, at least ideologically, we see a shift from the industrialized city with this chimney, smoke, air pollution, all grey, towards a greener landscape, quieter. Where we are heading? The future will be solar chemistry. The ambition is to use solar energy, wind energy to drive chemistry. However, there is still one problem. I have always been talking about linear exploitation, for the resources to the end product. For true sustainability, we need circularity. Think about a simple plastic bottle. This is made from basic chemical building units, by the way, still coming from fossil-based resources. Now, after its use, this plastic bottle should not end up in landfills or in the ocean, but should be put back into the manufacturing cycle. At the University of Salford, we are taking this challenge. We are developing new catalytic processes that are able to break down this plastic waste back to the building units or more complex molecules that can be used in other applications, including pharmaceuticals. Nowadays, we are called to think about alternative way of procuring our carbon source. We are witnessing effectively the energy crisis, which is due to our reliance on fossil-based resources. We are also called to reduce the carbon dioxide emissions, which are produced when we burn fuels. However, carbon dioxide can be our reagent, our feedstock. Carbon dioxide can produce back hydrocarbons by using solar energy. And by the way, this is a very intense research field nowadays. Think about waste. Our industry, agriculture, food, beverage industry, produce tons of waste biomasses per year. And too often, those end up in landfill. However, causing environmental damage. However, they are rich in chemistry. We could use this to get the feedstock for our current industrial processes. Or we can do something better. We can make completely new materials, new polymers, new fabrics with completely different properties, reflective properties, or just fancy materials, beautiful materials. Oh, I love that shiny dress. I love that dress with feathered fabrics. I want to buy one. So effectively, we need to transform the challenge of using a renewable feedstock into an opportunity for innovation and grow and create a completely different business product that wasn't there. And in order to do that, we need creative people. So up to this point, I have described what probably is our understanding of sustainability. What is next? Next is resilience. Now, the traditional chemical industry is based on large-scale, very complex, multi-step processes which are generally located in a remote area. They are optimized for a continuous supply of a feedstock, which is homogeneous in terms of chemical nature. However, circularity requires a completely different approach. Circularity requires that our system is adapted to the changing nature of this biomass, because or renewable source in general, because these are intermittent in nature. So we need to think about, we need to scale down our process. They need to be located ideally within the same context of where the waste is being produced. Now, the intermittent nature of the renewable resources is a challenge because the nature of the feedstock influences the efficiency of the process, and this has obviously an economical element in it. So what we need new knowledge. We need the knowledge that we need to cover a knowledge gap for this new requirement of dynamic chemistry. At the University of Salford, we make catalytic materials. What are those? They are particles, metal oxide particles, and what we do is we study the chemistry during the synthesis with the aim to control shape, size, morphology of the surface. And some of the particles our students prepare look like flowers, some look like popcorn, some look like perfect crystals. But what we are mostly interested in is actually the arrangement of the atoms at the surface, the structure of the surface, because this is what dictates the conversion of one given reagent into a specific product rather than another. And I'm sure that the bright spot here representing effectively atoms, they are very different at the surface from what you may have considered as for a round particle. Nowadays, we are in an extraordinary time for this kind of research because we have tools that can visualize atoms, electron microscopes. But we can do more. We can actually monitor how the atoms react in real time to give us, from a given feedstock, a product, a reaction product. So we are now in position to actually cover this knowledge gap and to be able to adapt the process and to modify the structure of the catalyst at the surface such that this produce the product we want, starting from one reagent or another. Now, still there are a lot of elements in the periodic table, which one we use and how we go about that. Of course, there is knowledge. We know which catalyst makes which reaction. But of course, nature is our best teacher. The problem of adaptation was already solved by enzymes, and I would like to, which are natural catalysts. And I would like to mention one enzyme, Rubisco. Rubisco is the enzyme responsible for carbon fixation, CO2, to glucose in plants, and therefore the building block, the backbones of our life on Earth. And this enzyme has been able to adapt to structurally change, very tiny structural change, such to optimize its efficiency and being able to convert CO2 to glucose regardless of the environment this is placed, regardless of the other molecules present. So if we can learn how enzyme works, we can translate this knowledge into the challenges of modern life, modern chemistry. So I would like to wrap up my talk now by saying that, again, we need new knowledge, we need creativity, but we need also everyone be involved, everyone with the chemistry mindset. We need to study chemistry from very early, ideally at primary school, to tackle the challenge of the future sustainable world. So that was Rosa Arigo thinking out loud. Thank you for listening.
Thank you very much.